Hello, everyone. Good afternoon. Welcome to our session. My name is Katie Carter. I'm from DeKema, located in Frankfurt, Germany, where I really focus on knowledge transfer between research and practice regarding wastewater management and circular economy. It's my pleasure today to welcome you to our session on safe water and how we propose to address the challenges of ensuring safe water and healthy ecosystems. If you give me a second, I will share my screen. So I hope now everyone can see it. So I want you to think about how we can address these challenges that we're being faced with today regarding water. And we propose that it's by taking actions. And taking actions can look differently depending on where you are, what you have, and what you need. And so today I'd like to introduce SERPIC. It's a project looking at treating wastewater treatment plant effluent for the safe irrigation of crops. Nanotech ABA, who's enhancing industrial wastewater reuse by implementing circular principles. Green Water Tech, developing water cleaning technologies via green solutions in green chemistry. The Pressage Project, who is innovating decentralized wastewater treatment. REVA, researching various systems for energy-efficient water purification. And the Nature Project, who is understanding and employing ecosystem services via nature-based solutions. Now, these 6 projects are all part of the Aquatic Pollutants ERANET Co-Fund. And so now I'll explain what exactly that is. So it's a European research network that was set up by 3 joint programming initiatives, Water, Oceans, and AMR. And in this ERANET co-fund, there are 32 national funding partner organizations that span across 26 countries, including the EU, Africa, and South America. And these funding organizations funded 18 research and innovation projects, as well as a transfer project, which I'm a part of myself. The 18 projects address 3 different themes regarding safe water. So that's measuring, evaluating, and taking actions. And you can see the descriptions there. And today we're going to focus on strategies to reduce CECs, pathogens, and AMR in our aquatic ecosystems. So here's a brief overview of today's session. These strategies will be presented in our first talk titled Different Water Scenarios Afford Specific Technologies to Remove CECs. And then we'll look into stakeholder engagement and implementation. So how can we move from research to operation? We will then end with a panel discussion with representatives from all the 6 projects. So please submit your questions in the chat box throughout the session to be addressed at the end of the session. And to start things off, I'll hand it over to Lars Österland from the Green Water Tech Project. He's a professor in solid-state physics from Uppsala University. And Nanette Zartman, she's from the Nanotech ABA project. And she's vice president of B4C in Denmark, which is a ceramic research organization. They're going to set the scene of this research co-fund. So Lars and Nanette, please feel free to take over.
Thank you so much, Katie. So it's a privilege now to be able to present the 6 different projects here from the Aquatic Pollutant Consortia. Setting the scene for this immensely important task is really a daunting task. But I mean, we are all aware from media and also maybe in our profession that water is becoming a very rare commodity. And recently, it happens continuously that you get these alarming reports. This one, which is shown here, is one of them, where it's showing that possibly 4 billion people lack safe water, which is defined in a specific way in this paper from a very recent study in Science. Of course, as many things, this impacts developing and low-income countries mostly. All these maps over the globe, they show different parameters showing this scarcity of safe drinking water. We're focusing here on the bottom right one, where we see the relative contribution of subcomponents limiting the use of safe water. And in red here, we have this contaminated water. You can see how this is distributed in these low-income and developing countries. And this red is then the alarming figures here. These issues has already been treated previously during this World Water Week conference, in particular one of the sessions, 11.804. But this is just setting the scene. More than half of the people on this planet are lacking safe water. And this is not only for drinking, this is for many usage. And you can see here that the shortage of fresh water here, another very recent study, that we are depleting the water coming from the natural groundwater, the aquifers around the world. And this is yet another very recent study. This is really alarming. But a good thing about this, if you flip now the slide to the next one on this animation, back a bit, thank you. This depletion, it can be stopped. I will not have time to go in detail into this particular study, but there are different color codes here as well, red and blue. The bluish is the one which is the promising thing. We can do something about it. We can stop it. We can reverse the process. It requires policy changes, how we treat water and we use water, but also technology, which is the subject of this presentation. Next slide, please. So compounds of emerging concern, CECs, which has now been highlighted as one of these groups of chemicals which are now been identified as harmful in our environment. This is one of the focuses of this presentation. And you can see here, if you start to skim through this image of this grand challenge associated with this, what do we know? This is a broad category of chemicals which are being detected in the environment. And they are called compounds of emerging concern because they cause some effects. And if you flip to the next one, potential impact on human health, wildlife, and ecosystems. And this is what we know. And why do we care? Of course, we should stop to pollute, but many of them are really persistent. We cannot get rid of them with the way we are dealing with water today. So this is really something which is at the center of this particular project. And they're not fully regulated or monitored. So this is also an awareness which is becoming widespread in the community. And that's why the CEC and the REACH and the United States and many others have now regulations starting to pop up in these areas. And this is the center of this particular topic. So next slide, please. So then I will hand over to my colleague here, Nanette, who will continue to define the different compounds and the origin of those. Please, Nanette.
Thank you very much. As Lars mentioned, it's a very diverse group, some of them being pharmaceuticals and compounds of personal care products. This includes antibiotics, which leads to increased levels of antibiotic-resistant bacteria and genes coding for antibiotic resistance. It is also endocrine disrupting chemicals such as BPA, which interfere with hormonal systems, and it could be PFAS, which interfere with cardiovascular health, nanomaterials, which is again a very diverse subgroup and very poorly understood, and microplastics, which interfere with our ecosystems. If we look to the next slides, then, well, where are they coming from? That's human activity. Most of us use personal care products and pharmaceuticals when we need it, because pharmaceuticals basically saves lives. Most of us have taken antibiotics at some point in our lives. Bisphenol and PFAS are example of chemicals that was once thought to be safe. Today they're banned, but they remain in our environment, and history is repeating itself with microplastics and nanomaterials. So what do we need to do for now and for the future? We need to clean up, because not all of this can be phased out. We need stronger risk assessments for new chemicals and novel applications for chemicals. And we need improved advanced treatment at wastewater treatment plants at point sources. Lars?
Yeah, we are coming now to the particular project where we are actually presenting the results from what we have done so far in this European effort in the cleaning up process. We offer new technologies here, and Paolo will in the next presentation exactly say what these 6 projects have done. And this is a range of technologies. And having said this, we emphasize that this is still on a fairly low level where it's not ready just to buy it off the shelf, but we are on the way, and this is the thing we will discuss, how we will exploit the results and how it can make an impact later on. And Marcus will discuss this later on. So this is a range of technologies, and I'll leave the floor to you, Paula, now to continue.
Okay.
Great, thank you, Lars and Annette, for that overview and kind of bringing us all together on the same page before we talk about the different technologies. So Paula, I'll just introduce you before you start your presentation. She's from the SERPIC project, so again, one of the 6 projects mentioned at the beginning. She's an associate professor in environmental and sanitary engineering at the University of Ferrara in Italy. And yeah, as the title says, Paula is going to walk us through the different technologies coming out of the 6 projects and how they can be implemented into different water scenarios. Okay, Paula.
Okay, thank you very much, Katie. Good afternoon to everyone. And my talk will be about the main peculiarities of 6 projects, including in this call, aquatic pollutants, and their capacity in trying to remove CECs. Before starting with the discussion and presentation of their main peculiarities, I want to bring the attention to the urban water cycle that is represented by the schematic that is reported in this slide. Go on, okay. You can see an arrow that represents the withdrawal from the aquatic environment. Its withdrawal will lead to the treatment and the production of drinking water that will be distributed and used by many users, and by means of their activities and the metabolic activities. It happens that many compounds, many pollutants are added in the water, and there are different categories. Most of them are well known: suspended solids, inorganics, organics, but also CEC and AMR. This is unavoidable. And the wastewater produced at the different levels is conveyed and treated in centralized wastewater treatment plant that were conceived to remove conventional pollutants, regulated contaminants, such as suspended solids, inorganics, organics compounds, and also bacteria. But they are not able to remove the wide spectrum of CEC that are present in the influent to the wastewater treatment plant. And so they are still present in the final effluent. So CECs and AMR are present in the final effluent that is generally released in the environment, or in some cases destinated to be reused for different purposes, mainly for agricultural purposes. In this way, we have the spread the spread of contaminants of emerging concerns and AMR in the environment through the reuse or also to the discharge. The next one, thanks. Okay. And the projects we developed intervene in a different point, at different points of the urban water cycle. So look at the water sources. We have different kinds: the household, industry, hospital, the land and its runoff, and the environment, mainly the surface water. And our attention is to be able to produce a final effluent to be destinated to the reuse, the direct reuse, or to be discharged, released in the environment. And the idea is to promote, safeguard the environment. And it is unavailable that the contaminants are present in the water source And there are available existing wastewater treatment plants that are able to remove some contaminants, but not all of them. So the project we developed in these 3 last years are able to act as additional treatment at the end of pipe treatment of the existing wastewater treatment plant, or to improve, to change, to promote the biological treatment in advanced biological treatment, or alternatives to be useful for the improvement of the surface water. And in this case, the last option, they are fed by surface water. The common goal is the reduction of a different kind of contaminant of emerging concerns. But the next one, please. But if we look to the project and their development, we have many conditions to consider. These are the boundary conditions that interest the water sources, in particular the different regions, the different countries, and the different consumption patterns of the different compounds. So it is important to select specific target compounds to monitor and thus to evaluate the capacity of new technologies to be able to remove them. And during the development of the novel treatments, we have to consider that compounds may have different behaviors due to their very different characteristics. And so the systems, the new system must be multi-barriers, that is able to put different removal mechanisms, able to remove them, the different types of microorganisms. They must fit to the local condition, and so centralized, decentralized, modular systems, and hopefully they must require low energy, no chemicals. Maybe it is useful they are able to use upcycled materials, to respect standards, and also to integrate in the landscape. It is also important to evaluate the behavior of the contaminants, and so to monitor the transport and the fate of contaminants, mainly in the case of direct reuse of the final effluent. And regarding the final effluent, we have to respect, where available, regulations, and also to implement the principle of guidances that are available, such as the One Health and the different action plans. So we can have go on with the European Green Deal, Zero Pollution Action Plan, and so on. So look at the next one. So looking to the details of the different projects, starting with the SERPIC, we have that the water source for this project is the secondary effluent of a wastewater treatment plant. And so this is end-of-pipe treatment. And it combines physical processes, nanofiltration membrane, and chemical processes, namely oxidation, by means of electrochemical generated ozone gas for route A, for the permeate of the nanofiltration step, and the oxidation by means of electrochemically generated persulfate for the concentrate of the nanofiltration step. Both the stream, the final effluents, are able to be to respect the environment in terms of the reduction of CEC, and in particular, the first one can be used for direct irrigation, and the second one can be directly released in the environment. And the respect is demonstrated by the removal efficiency achieved with reference to the selected contaminants, diclofenac, venlafaxine, iopромide, sulfamethoxazole, and the bacteria E. coli and the gene with resistance to antibiotics, SUL1. The removal efficiency are quite high. Only venlafaxine presents a lower value and demonstrated to be the most recalcitrant persistent among the selected compound. The peculiarities of the system is a multi-barrier, low energy consumption, low need for chemicals, and show case locally. The next project is nanosec ABA, and is similar to the septic one because it is the end of pipe treatment and is fed with the secondary effluent of wastewater treatment plant and also by industrial wastewater. And it consists of a three-step treatment consisting of physical processes, a combination of membranes and chemical processes, oxidation. The membranes, in particular, the microfiltration membrane is a modified antimicrobial microfiltration membrane able to reduce the fouling of the membrane itself. The second type of membrane are ultra-stable silicon carbide membranes, and the oxidation is achieved by means of nano-enabled thermocatalytic packed bed reactor, able to attack CEC and remove them, as well as antibiotic resistance bacteria. The compounds selected for monitoring and evaluating the removal is a plastic additive bisphenol A, and it was found a removal efficiency up to 90%. The final effluents of the two stream, again, the permeate and the treated concentrate are irrigation, industry, and environment. The next one. Green water tech uses a combinations of green chemical processes for final water cleaning, and it wants to treat surface water. The combination consists of chemical processes, a nanoabsorption, enzymatic cleaning, and the photocatalysis step. It was found that with regard to different kinds of pharmaceutical, most of them are very persistent, such as carbamazepine and also diclofenac, are able to be strongly removed with a removal efficiency after the three-step train even more than 99%. And the final effluent can be used for irrigation, aquaculture, environment, industry needs, and drinking purposes. This is a multi-barrier system characterized by a low energy consumption and a low need for chemicals. The next one. The next one is Presage, and the peculiarity of this project is that it applies to raw industrial wastewater and hospital wastewater, or black water and grey water. So the water source is not the secondary effluent, but the primary effluent, we can say. And it consists on a combination of different types of biological processes combined with, in some cases, physical processes and chemical one. The biological processes may differ because they can have membrane bioreactor or moving bed bioreactor or structured bed reactor. In some of them, membrane bioreactor, the separation between the liquid phase and the solid phase is characterized by the use of membranes, microfiltration and ultrafiltration. Thus, physical processes are combined with biological process. And in some cases, there is also the need for a disinfection, and in this case is achieved in a particular bed biocidal reactor. The evaluation of the performance was referred to antibiotics, ciprofloxacin, trimethoprim, sulfamethoxazole, to two bacteria, Klebsiella and Enterococcus, and to 7 germs. And the results are quite promising, really promising, because it seems the system is able to remove up to and more than 2.53 log units for bacteria, more than 3-4 log units for AMR, and between 75 and 90% for antibiotics. These systems can be decentralized applied because it is able to be realized in small size and can reach scattered house and not only larger wastewater treatment plant. Is a multi-barrier, low energy consumption, characterized low need for chemicals. The next one. Riva uses chemical process based on natural materials, and the water source is the secondary effluent of a wastewater treatment plant, also industrial wastewater, as well as surface water. It consists of three options. We can have in all of them chemical processes. In the first step, in the first option is absorption of natural bioabsorbents. In the second, the biocoagulants for the removal of metals. In the third one, we have a photocatalyst for the removal of contaminant of emerging concerns. They selected a long list of CECs and vanadium. And regarding the selected for this slide contaminants of emerging concerns, the removal varies depending on the compounds, between 71.4 and 99.7 for the different antimicrobial or antibiotics, and for regarding AD1. Regarding the second option, vanadium was removed more than 88%, and regarding the third option, the antibiotic tetracycline around 93%. The final effluent can be used for drinking purposes and for the environment. The next one. Nature is another project that uses nature-based solution, different types of nature-based solution, bioelectrochemical treatment of wetlands, or vertical flow treatment wetlands, or aerated treatment wetlands, or horizontal flow constructive wetlands, surface flow constructive wetland, different type of wetland, restored wetland or river renaturalization systems, and finally vegetated and no vegetated salt marshes. The investigation considers mainly pharmaceuticals, in particular antibiotics, and two genes with resistance to antibiotics. And the removal achieved in the different options regard acting as secondary, tertiary treatments for the wastewater treatment plant or surface treatment in the case of surface water as a feeding. The removal efficiency varied depending on the compounds, from the 50% for doxycycline to 99% for clarithromycin. And the removal may be variable depending on the specific option for the same compound. For instance, clarithromycin may vary between 18 and 99%. The final effluent can be used for irrigation or the environment improvement. The peculiarity of the project: low energy consumption, no need for chemicals, landscape integration, multi-barrier systems, and also the characteristic of being showcased locally. So, if we think of the overview regarding the 6 projects here analyzed, we can say that the boundary conditions that strongly changed from one project to another one provided some hints for the development and were strongly considered in the development of the technology, also with the consideration of the different water sources that represented the feeding of the different treatment plants. And in any case, we found very good results for the final effluent for the different destination reuses or uses. And in the following slide, you can see how was important the opinion of stakeholders, and how was important to implement the hints, the suggestions of the local country, the local consideration, underlying the importance of the boundary condition in any phase of the development of this project. Thanks for all.
Thank you, Paola. Summarizing 6 very complex projects, very different projects in 15 minutes is quite a feat. So thank you so much for that brief presentation and an overview of the different technologies coming out of aquatic pollutants. So now I'd like to shift to thinking about the science to policy pipeline, which can be quite complex. There are a lot of questions. What does this pipeline look like? Who is involved? What information is needed? And to shed a bit of light on these questions is Markus Grunewald. He's the CEO of Nanoform Science and an expert in bringing new innovations to the market. So Marcus, take it away.
Yeah, thank you so much. Yes, as mentioned, we have been involved in the Green Water Take project as a partner, and we are now focusing more and more on bringing the results to active use. And so one of the key things I wanted to bring your attention to, that I'm sure most of you are aware of, but it's worth still being reminded of, is that the outreach to stakeholders is an active part of a formal part of any EU project. We are required to highlight how we will engage with stakeholders of various kinds and what the message and the tools will be. So this is not something that we can just kind of ignore, but it's actually an active part of the process already from the start. Now, what's changed over the years is that we moved, or the EU has kind of highlighted the need to move from information sharing to creating an active process of engagement with future users. So you can look at the next slide, please. So the idea is that we need to have a two-way process of exchanging information. Now, the question is, how does this kind of come to realization? Obviously, depends very much on the type of stakeholder group that we're engaging with. But also, we sometimes feel that or we see that there's a lack of understanding of what message each stakeholder group is actually needing in order to kind of pursue and engage with a project. So it's very important that we also get an understanding from the audience. What are you looking for? What are the questions, the parameters, and criteria that you work with in your daily life? Next slide, please. So the key message for us, as you know, and talking with one voice here, but representing 6 projects, is that we have reached key goals. We are now in a position, as Lars mentioned earlier, where we could start reversing, processes that a lot of people think are difficult or impossible to change. Continue, please. The fact is, I'll go back, sorry. So the message is really that we have seen a substantial reduction in pollutants, as we saw in the previous presentation, of various kinds, and there's different types of technologies, and obviously targeting different types of end users, and obviously all of you might be looking at different types of technologies in your operations. But the question now remains: how do we move from a situation where we have got these kind of key goals and results on an R&D process, where the question is, what are the scale that we've achieved so far, and what is the scale needed at the end? But also in between, how do we validate a commercial unit? Does it need to involve the final scale size, or are there in between steps that we can utilize together that allow the end users or US stakeholders to feel confident in the technologies? So these are the type of challenges that we are all kind of facing when we work with EU funding, but we are now seeing this more and more as a process that needs your active engagement if we are going to be able to accelerate the move from the R&D phase to active implementation. Next slide, please. So again, the complexity lies very much in the type of technology used, but also the type of end user applications that are engaged in this. And today we have reached a process where we focus on R&D. You can continue, please. But as I'm sure you understand, the type of activities now being accelerated involve a wide range of different type of activities if we're going to take these kind of R&D results towards active deployment. But not only does it involve different type of processes, but also different type of stakeholders. And this is where we really want to push the message that it's only with your active engagement, the questions raised, the commentary from you, highlighting your needs, that we understand and can kind of prioritize the development of answers to these kind of questions. Because the type of stakeholders ranging from academia to industry to payers to regulators all needs to be taken into account. And our hope is that we can jointly present a more coherent message where you as a stakeholder feel that there's a need and a place for you to engage already now, rather than wait until the end, and where you can kind of perhaps normally or naturally assess the results. But hopefully we can create a channel for you to join in now when we accelerate towards future deployment, and with your help accelerate this process even more. Next slide, please. So what we need to kind of understand is that this process, although it might take a long time, can be accelerated. There are a lot of conditions that needs to be fulfilled, but it's also not a linear process. We all need different things. And so, for example, we've highlighted here a few different activities that we're now engaged with, depending on the product level. So, for example, Serpic, the project, is now looking for manufacturers of water treatment equipment in order to kind of develop the technology further and move towards demonstration. The nanotech CEABA project wants to kind of move towards long-term studies and the techno-economic analysis together with end users, so that we can kind of create a more coherent understanding of what's needed for the next step. Our project, the Green Water Tech project, we are looking to engage with various end users of different scale, so we understand which one we should prioritize, and also understand the kind of challenges that might occur when we kind of scale up towards a commercial product. The Presage project, on the other hand, also wants to engage with problem owners. We need to understand what are the conditions facing you today if you represent the industry of the wastewater companies. What are your focuses and priorities, and so forth. Reva, again, is looking at research around the scaling up and all the cost-benefit analysis related to this. Also here, long-term studies and case-specific solutions will be necessary together, again, with you as a stakeholder. And then finally, nature is looking to actively communicate and disseminate the findings so far. We need to explain to society, but also policy representatives and regulators, what the benefits are with nature-based solutions, but also understand the potential barriers to entry. What's stopping society towards utilizing these type of technologies? There was, for example, a question raised in the chat about the use of these type of solutions in developing countries, and it's a very fair point. The potential for paying for technology is going to vary greatly even within the EU setting. So how do we ensure that we maximize the impact of these technologies for EU the EU water systems? And again, it's only with the joint collaboration with US stakeholders that we can achieve the reversal of the depletion process that was mentioned earlier. We need to understand your reality, and also make sure that we focus on developing answers to the key questions that are raised first and foremost. Next slide. Yeah, so again, we are all actively looking to engage with you. We will have our contact details available, and we're all hoping that we can to find and have an active communication with you. We will also try and reach out to stakeholders of various kinds ourselves, of course. But again, we hope that you feel interested enough in our products to leave us your contact details, and also what your interests are, and we can hopefully then kind of create a more active two-way communication with you moving forward.
Great. Thank you so much, Marcus. With that, we can officially start the panel discussion and audience Q&A portion of our session today. So I think everyone already has their video on, all of the participants in the panel. So I'll start off by introducing those people who we have not yet heard from today. As I said, we have representatives from all 6 projects joining us. So first we have Jan Gabler. Maybe you can wave your hand so they know which box to look at. He's from the Serpic project. He's a project manager at the Fraunhofer Institute for Surface Engineering and Thin Films in Germany. Then we have Henrik Rasmus Andersen. He's from the Presage project. Thank you. Professor in the Department of Environmental and Resource Engineering at the Technical University of Denmark. Then we have Victor Matamoros. Hello. From the Nature Project, looking at nature-based solutions. He's a biochemist and biologist at the Spanish National Research Council. And then we also have Ani Vadanyan from Green Water Tech. She's a postdoc researcher in the area of inorganic and physical chemistry here in Sweden at the Swedish University of Agricultural Sciences. So thank you, everyone. And of course, we're joined by our speakers who gave talks earlier in the session. So I know that we have a few questions in the chat, and Marcos, you kind of touched on one already, but I was wondering if anyone else has something to say about the affordability of treatment steps for CECs in developing countries. Does anyone have any further input on this question? Okay, doesn't seem to be the case.
If I recall,
Josh?
I mean, I was just clicking, I was unmuted. But if I recall the question, it was also about the cost benefit, which also Marcus touched upon. And this is actually a multifold question because, of course, at this scale, as also Marcus mentioned, some projects are in the process of doing the cost analysis and technical economical analysis. But some projects are actually from first principle designed to be cost efficient. So the answer, a general answer to the question is that these kind of projects which have been presented, they have already at the outset been designed to be cost efficient as much as they can today. And then when it comes to deployment and upscaling, this is an issue which is beyond what we are reaching in the project, and we will see what happens. But per se, there is no reason why they could not be affordable for developing and low-income countries.
Thank you. And then maybe we move on to the next question from the chat. So looking at what are the most problematic CECs? I know this conversation came up in earlier meetings that there are already existing technologies to remove CECs. But maybe Jan or someone else wants to speak to this about what differentiates your technologies, or where are the trouble points, so to say, removing CECs?
Yeah, I would like to forward the question to Paola. I think she's better able to answer. Paola, may I?
Yes, I can try to reply to this point. The main problem is that we have a large spectrum of compounds in wastewater, and there are many compounds of different characteristics, and the system must be a multi-barrier, able to promote different removal mechanisms. We have that these contaminants may vary their concentration over the year. So it is not right to think to one compound, to the most persistent, and to try to remove it at the lowest level, because we have many other things that may happen over the year. So we have to select a group of compounds depending on the region, depending on the country, study the situation and the data set of the last year, the years, and to see which can be the compounds of relevance for that area, and evaluate which could be the main adequate removal mechanisms, and select the treatment depending on this. Okay.
If I may,
Thank you.
can I add to this? A very, very good answer, Paula. But if I recall the question, it was very specific about compounds. There is actually a very specific answer also. Humans, we have the inclination to try to beat nature. Plastics is one of the innovation from the mid 20th century, and they are designed to be very persistent. And so everything related, so bisphenol was one of these guys where you find it in plastic bottles, and there was an issue that baby bottles, they carry these bisphenols and then they can be harmful. And they are by design made to be very persistent. Pharmaceuticals also carry these properties. They are designed to be very persistent to biochemical processes. This is why we make them to be persistent. And by the same token, they become persistent to natural degradation processes. In Sweden, we have lately this PFAS problem, perfluorinated hydrocarbons. And especially the small ones, they slip through the ordinary treatment, adsorbent filters and so on. And from a chemical viewpoint, they are these aromatic molecules where they, by chemistry, are very resistant to oxidation processes. So this is a very general answer, but as Paolo said, you need to be very precise. And this is why Marcus tells you that we want engagement with the stakeholders. But there are class molecules where mankind have made very persistent molecules, which escapes natural own processes. So this is sort of a general overarching answer.
This makes me think of looking in the direction of kind of risk assessment. So also focusing on which ones are the most persistent, which compounds may have pose the most risks for human health and also the environment. And Victor, I want to look in your virtual direction because I know that your project also looked into the reduction of risk via nature-based solutions. And one thing that I heard here at World Water Week is that research, so policymakers can really look to researchers for pointing out where risks are and where focus should be placed. And so I was wondering if you could just tell us about your project's work in examining this reduction of risk to human health and the environment via nature-based solutions.
Well, thank you, Katie. So, well, in the frame of the natural project, we have evaluated the ecological risk associated with the implementation of various natural-based solutions for wastewater treatment across different trophic levels, including green algae and also fish. Our findings indicate that compared to conventional tertiary wastewater treatment based on the combination of sample filtration, UV, radiation, and culmination, natural-based solutions offer a greater reduction in ecological risk to levels where the risk is not present, so this is good. Additionally, the microbiological communities in natural-based solutions shift from wastewater-related microorganisms at the inlet of the natural-based solution to those typically found in natural surface water bodies at the natural-based solution water effluent. This discharge or this change in microbial communities is not observed with conventional wastewater treatments, where wastewater-related microorganisms are discharged in our water ecosystems. This suggests, again, that the use of natural-based solutions has a little to no impact on the aquatic ecosystem, so a positive impact if it has some impact. This is the main reason why, in the frame of the Natural Project, we want to recommend the implementation of natural-based solutions as a buffer between an existing wastewater treatment plants and surface water bodies. This will minimize and reduce any potential chemical or biological risk in our aquatic ecosystems.
Great, thank you. And then I think I'm going to skip one of the questions in the chat. I'll come back to it in a second. But I think this one kind of plays off of that. And maybe, Jan, you have something to say in this direction. So David Sarfi from Aquafirm, he's stating that the World Health Organization has called AMR, antimicrobial resistance, one of the 10 biggest threats to humanity. And this could mean that in the future antibiotics stop being so effective. Do you have any ideas on how outreach activities could be used to make industry, water utilities, or the public aware of this demand or need for new technologies? Or what is your experience including or reaching out to stakeholders like these groups in your research? Yeah.
Yeah, well, we are a researcher for water treatment technology, so probably it's not our first goal to reach out to public for AMR. But as you know, there are also other projects of the Aquatic Pollutants program who are addressing exactly this topic about the presence of CECs and AMR and about the evaluation and the risk assessment. So I'm sure that they will have ideas about that. But to be honest, I have no ideas on that question. Sorry.
But you yourself in the SERPIC project engage with stakeholders and have also a long list of stakeholders. So maybe you can say more about how you have engaged with stakeholders to show them the research that you're doing in SERPIC.
Yes, that's true. We in the proposal phase, we collected quite a huge number of stakeholders, more than 40, who had interest and signed letter of intent. So, but in the practical implementation, it came out that it was not so easy to interact with them. One very practical reason was that some of them are not good in English, and of course we wanted to communicate in English. So it came out that we need to rearrange our concept. And this is what I learned also from this project, and I will reflect it for future project, that it's probably better to interact with them on a national basis, with the national partners in each country, and also with the language that they are speaking, and using also existing relationships to build up on this stakeholder interaction. This might be a better concept than to have a central communication via newsletters and probably a big joint conference, which would not be so efficient to my experience.
Right. It's been going back to the point from Marcus' presentation, not only dissemination, but two-way engagement. And Marcus, you have raised your hand, so you can respond.
Yeah, I just want to add another thing that's almost forgotten is that we find that the stakeholders representing water in the industry in Sweden, where we're based, themselves have a very interesting ecosystem or engagement, sometimes even with the developing world. So my local municipality work actively with water questions and challenges in Uganda. And this is kind of starting to become a two-way process as well, where we're learning from these type of regions how they deal with water scarcity and so forth. So I think also it's important for us to let our stakeholders know that we're also interested in understanding who they communicate with, not only regionally, but of course even here where they have to work within a system with other actors that work with water. So we want to reach them as well. So it's not only the direct dialogue with stakeholders that we identify, but also to understand who they in turn engage with. That for us is very, very interesting and very exciting if we can kind of get access to them in that way.
Great, thank you. That's also a good segue into this final question that we have in the chat. And Annie, I'm gonna look in your direction as our representative young researcher in today's panel. So the question is, so we want to initiate this two-way engagement with stakeholders as part of technology development. And from your perspective, how can academics train the new generation, maybe you consider yourself a part of this, to have these skills that are needed to reach outside of the research bubble?
That's actually such a hard question for me personally. Social skills developed when I went to study abroad, basically, and going to conferences, meeting, as you said, the stakeholders there, or joining to panel sessions like this and talking. This is the way to develop these social skills. And I guess if I am going to train the future generations in the university, that's the only way, just to take them to the meetings, to the conferences, and so on.
Great, just kind of throw them in and learn how to communicate. I think that works. So there's one question in the chat regarding PFAS, and I know that that's not a huge focus of the aquatic pollutants projects, since we mainly focus on other contaminants of emerging concern. But there's a question regarding if any one of you has an opinion on the current discussions going on at the EU level regarding PFAS, for example, with the new urban wastewater treatment directive. I don't know if anyone wants to say something about that. Paola?
Yes, PFAS represent a very problem in many countries because they are present in any water compartment, and depending on the final destination, the problems can be of great concern. Regarding emergency situation, for instance, if it is we found that PFAS are present in water withdrawn for drinking purposes, we have an emergency action to stop them, to remove them by activated carbon, for instance. But the life of activated carbon is very, very short, and so the system is the system to remove them is expensive, because with high frequency carbon must be regenerated, not regenerated, but replaced with a new one, virgin one. So PFAS represent a hot problem in this moment, because we don't have an economic cheap systems to remove them in drinking water just before the distribution, or in wastewater. One possible action could be the reduction at the source. So try to remove the presence of PFAS at the source and reduce the influence, the emission in the environment. This can be one solution, one possible action. But PFAS are the current, one of the current main concerns regarding water and wastewater treatment. But other compounds can have a similar concern in the coming years. And it is important to go on with the research, with the technologies able to remove them, in finding also analytical methods cheaper. And to monitor the situation and to guarantee that the system is under control, and that the distributed water is safe, and immediately we can act to preserve water and safeguard human health and also the environment. Now, PFAS represent a great concern, but I think that in the coming months, in the coming years, other compounds can have the same concern or similar concern, depending on the effect. Because, for instance, in Italy, we have a region where there was an industry that released a large amount of PFAS in the river, which was used for drinking purposes, and the local population had many cases of disease, serious disease, death. And so for some regions is a hot problem, an emergency, absolutely an emergency. Not if the level is very, very low, but in that case, the concentration was very high.
Lars, do you want to say something really quickly to jump off her answer? You're still muted.
I raised my hand before Paula expanded on her answer, but PFAS is one of these CECs which we have been addressing in these aquatic pollutant products. So it's indeed very important. Banning is probably happening, but it also has an economic impact because it's used in industry process. A replacement of these chemicals is must go on parallel. This is what I've seen before, but legislation will probably happen sometime.
Okay, unfortunately, we are almost out of time. Henrik, I don't know, regarding this PFAS conversation. So Paul also said, like, we're looking, it's a lot of a reduction of the source, so from the production of PFAS, and in Presage, you are working with hospital wastewater, so also looking directly at the source. So what does this collaboration with, you know, the source look like? We won't call them polluters, but what, do you have any insights that you want to very quickly share?
Well, the collaboration for hospitals and these industries, it comes two ways. They don't want to be known to be a point source, so they want to spend money on treatment and on looking for solution. But there's also a lot of push from the regulators because you need to have a permit to be connected to the sewer. If there's a special chemical, this can be causing extra cost, or that you simply are not allowed to connect, and then you need a treatment like what we're working with. We also, not in the Presage, but other projects, we have source treatment for PFAS, especially solid waste dump site are the main source into the sewer system for PFAS. So if you treat there, much less come to the sewage treatment plant and end up in the sludge.
Great. Thank you for that brief word. Then with that, I will end today's session, and I just wanted to then put this QR code back up on the screen, which is our website and also our contact information. You all are already online, so don't go far. There is a session starting right now, also on aquatic pollutants projects with partners located in South Africa, looking at how they're using their technologies to solve South African water challenges. So thank you so much for being here, and thanks for the questions.